Are we inside or outside? Yes. Interstitial fluid is outside the cell. So interstitial fluid is actually a type of ECF. ECF stands for what?
Extracellular.
Extracellular fluid. So right now we're in the fluid outside your cells. We're in a type of your extracellular fluid compartment. So interstitial fluid outside your cells is a major site for sodium and calcium ions. It's tempting to memorize this list, and I completely understand it's hard to keep all these ions straight. But if we talk about this and we think about the locations of these ions, really most of what's up here makes good sense. Calcium, let's start with that one. Calcium is a major component of what? Bones. Okay, so in order to get calcium from your bones, we release it into the bloodstream or the interstitial fluid. So calcium actually is one of those extracellular components, not intracellular. It's outside the cell, so we majorly store most of our calcium ions. Sodium is mostly on the outsides of your cells, and a good way to think about this is going back to Bio 210. In Bio 210, we talked about sodium being on the outside of muscles and nerves. When those sodium gates or channels open, sodium rushes into the interior of the cell. So if you just think about normal conditions, resting state conditions for muscles and nerves, sodium was always on the outside of the cell. Here you go, interstitial fluid is outside the cell. Just a comment there about sodium levels. Sodium levels tend to stay fairly constant, even if you take in salt or if you lose salt from your body. And I'm using the term salt there to mean things like sodium or chlorine or potassium. So that category of salt is a very generic category. But nonetheless, sodium levels tend to stay pretty constant in our bodies. Why do you think they need to stay pretty constant?
Action potential?
Action potential, yeah. Muscle conduction, nerve impulse transmission. If you have constantly fluctuating levels of sodium, then your muscles and nerves will suffer as a result. So, got to have a fairly constant level of sodium for proper neuromuscular function. Let's see. Last Thursday I shared with you my little trick for remembering intracellular cations. Potassium has a symbol of K. Magnesium has a symbol of Mg. So you'll notice here that potassium and magnesium, the word potassium starts with a P. Magnesium, of course, starts with an M. I keep that straight because they're inside the plasma membrane, PM, plasma membrane. So these two ions typically tend to be intracellular ions. We haven't talked too much about magnesium in this course, but boy, did you talk about potassium in Bio 210, right? So that's one of those major types of ions that stays inside your cell. It helps to maintain resting potential as long as potassium is inside. So here again, it's just, thinking about what you learned before, not necessarily a thing to memorize, but just think about where you've heard of potassium in the past. By the way, where is most of our fluid housed?
Inside of the cell.
Inside the cells. So you can see another role of both potassium and magnesium is to maintain water balance inside the cell. What do you think happens if you lose a bunch of your potassium? What happens to your water? Yeah, it leaves, you become dehydrated. So actually, in addition to maintaining resting potential for muscles and nerves, we also need potassium to maintain water balance inside our cells. And heck, you're storing about 2/3 of your water inside of a cell. It's pretty critical that you have enough potassium there to hang on to that water and keep it inside the cell. These are somewhat new for us. We haven't spent a whole lot of time talking about anions. Anions, of course, with a negative charge. In the interstitial fluid, we have chlorine. Give you a clue here because salt, plain old table salt is sodium chloride, right? Notice what's out there in the interstitial fluid, sodium. Oh, that makes sense, right? Sodium and chlorine tend to be in the interstitial fluid because they're old buddies. They're what essentially breaks apart from table salt. Bicarbonate, another friend for us from the respiratory chapter, bicarbonate is actually formed from what gas?
Dioxide.
Carbon dioxide. So it acts as a buffer in our bloodstream. So you can't really have this inside cells, you need to have this outside cells, because to buffer your bloodstream, you need this readily available to the blood so it can monitor and kind of shift that blood pH if necessary. So think about bicarbonate, think about carbon dioxide, think about a buffer for the bloodstream, and that will remind you it's in the interstitial fluids and not necessarily the intracellular fluids. We haven't talked at all about phosphate. It is one of our pH buffers. We'll talk about that on Thursday a little bit. But we have other buffers in our bloodstream that help to maintain blood pH in addition to bicarbonate ion. So phosphate is actually a blood buffer, maintains pH within that narrow range of values. So it is stored inside cells rather than outside cells, so just something to kind of keep straight there. Barbara?
What does magnesium do for
it's more of a resting state ion. When we talked about resting state for muscles and nerves, we didn't ever mention it, but it's necessary to have it in there to maintain resting potential. So, like women who are going into early labor, they'll give them magnesium, and that helps to actually lower the, make more negative the interior of the cell. It makes the cell stay at rest rather than being excitable and producing early labor contractions.
So why would they give you magnesium sulfate if you was already in it, like full terminal?
Maybe to slow down contractions. I don't know what. If you're actually supposed to be going through labor, I don't know why they would give it to you then. But
they had given me. Remember when you showed the pictures of the brain swelling and stuff?
Right.
They were giving me magnesium sulfate to make my brain stop swelling, but it wasn't working.
Obviously had something, if they were giving that to you for cerebral edema, something to do with maintaining a fluid balance, perhaps pulling the fluid off your brain.
That's what I thought, but maybe like that helped with that.
Yeah, it's this. See, there's a difference between magnesium sulfate and magnesium ions because they have a different pull value. Because magnesium sulfate ionizes into magnesium, sulfur is an oxygen and sulfate, so to speak. So that might have had a different value in terms of pulling fluids in a certain direction. Correct. Obviously, in that case, off your brain. So you actually asked a pretty relevant question there because at the bottom of your page, you might notice we're going to talk about osmosis and electrolytes and milliequivalents. We briefly touched on this last class period, but we didn't get to spend enough time with it, so I want to take you back to the bottom of your page. The reason we're talking about these electrolytes is they all have some role in water pool, which is osmosis, of course. So we're trying to maintain the fluid in our particular compartment, whether it's intracellular or extracellular. So these ions all have a certain pull value. What I mean by pull value, they have a measurement here in milliequivalents per liter. And the more solutes you have in a particular compartment, what does that mean about the water movement?
More water.
The more you pull in the water, exactly. So here's something that's kind of an interesting concept. As ions, as sodium ion, potassium ion, and so on, these ions have more of a pull on the water in the surrounding areas than does something like glucose. Back in Bio 210, you might recall we talked about ionic bonds and covalent bonds. Inorganic compounds are things like acids, bases, salts, electrolytes. They're all ionically bonded together. Covalent bonding was common in organic compounds. What were some examples of organic compounds? Glucose, protein, any kind of fat, any kind of sugar, in fact, is a covalently bonded molecule. I make this point because if you have a covalently bonded molecule, it does not ionize or break apart into parts. So if you've got glucose, for instance, let's get some chalk. Glucose placed in water does not ionize into carbons, hydrogens, or oxygen. Glucose placed in the water simply stays in its whole form. Table salt, however, place that into water. Table salt is an ionically compounded molecule, so it's going to break apart into its two ions, sodium, of course, and chlorine. So in terms of pulling power, glucose is simply identified as one unit because it does not break apart into any kind of, ionic component. But look at this. Table salt breaks apart into two components. If you're talking about solute concentration, this gives you more solutes in terms of solute concentration. So in terms of pulling power, which of these two molecules actually is going to pull more water to its area? Sodium and chlorine. Yeah, because you've got more pulling power just by having those two ions created. So the concept here is that if you have a covalently bonded molecule like glucose, it has less power to pull solutes than do ions and ionically compounded molecules like acids, bases, salts, and electrolytes. So all of these items that you're looking at up here, magnesium, calcium, potassium, sodium, we just did all those. Phosphate, bicarbonate, chloride. We didn't talk about sulfate, but there you go, another one of those ionic compounds. These all have more pulling power in terms of osmosis because they increase the solute concentration in a particular compartment. Dwayne.
But did we say that the sodium follows the glucose? The glucose follows the sodium?
It does follow the sodium, and it's a protein that couples the movement of both of them through together. So in terms of the kidneys, that's kind of I guess you'd say an exception to the way they work.
Okay.
Yeah.
We can spill more water or fluid?
All of these.
All of them.
All of them.
Okay.
The proteins in their whole form, like blood proteins, they also create pull, and then some